Hi, today I'm going to talk about round versus resident trade-offs for binary channels with feedback. This is joint work with Mark Braverman, Klim Efremenko, Gillat and Raghuvansh Saxena. Hey, let me first start with a brief review of what is error correcting code. So the test is pretty simple. Alice wants to send some message to Bob over some noisy channel, which can corrupt part of the message she transmits. And so Alice just encodes her message using some error correcting code, and so that Bob can still successfully decode to the right message, as long as there are not too many corruptions introduced in the channel. So the question we want to ask today is, does it help if Alice is given access to feedback, which basically means for every bit she transmits, Alice knows what Bob receives. So this question has actually been studied previously. So in 1956, Shannon says the answer to this question should be no if we consider stochastic channels where, like, for each bit sent by Alice, it's randomly corrupted or not with a certain probability. And he shows with or without feedback, the channel capacity remains the same. And a few years later, Berlekamp also says the answer to this question should be yes if we consider adversarial channels, which basically means we have an adversary which can corrupt any bit he wants, as long as the total number of corruptions is below a certain corruption budget. And he shows we can achieve a better error resistance if we are given feedback. And as a warm-up, we can first check the simpler erasure channels. The protocol is pretty simple. Alice can just repeat the same bit she wants to send until Bob receives that bit. And then he tries to send the next bit. So this way, we can increase the resilience from 1/2, which is achievable by classical error correcting code, to 1. And what Berlekamp essentially does is it shows for corruption channels, we can actually extend the above ideas to design what we call rewind with error protocols. So by rewind with error, we mean when Alice detects there are some corruptions, he can send some special stuff to Bob so that they can rewind to a certain point in the previous execution of the protocol. And this way, he shows the resilience for corruption channels can be increased from 1/4 to 1/3. However, for both of these protocols, there's a major drawback. That is, we assume full continuous feedback. Or we mean the feedback is real time or instant, in the sense that Alice will know what is received by Bob immediately after she sent that bit. So as you can imagine, such type of feedback can be very costly to implement or even impossible to implement in practice. So in this paper, we want to study what is a limited feedback by introducing the concept of round restricted feedback channels. So for a round restricted feedback channel, Alice will send in R+1 rounds. So in every round, Alice first send message of certain length over the noisy channel. And only after sending all the bits for that round will Alice learn what is actually received by Bob in that round. So the feedback is given to Alice round by round instead of immediately. So the main result of our paper shows for binary erasure channels, the max resilience is actually 5/7 if there's only one feedback round. And when there are more than one feedback round, the match residence is 1 minus 7 over 12 times r plus 1, which converges to 1 inversely in the number of feedback rounds. And also for corruption channels, it turns out it's much harder than the erasure case. And for the simplest scenario of a single feedback round, we show that the match residence is upper bounded by 7 over 23. And we also believe this 7 over 23 is a tight bound. We designed a protocol which we believe is optimal, but we cannot actually prove it. We only show that it's equivalent to a purely graph theoretical conjecture about match cuts in weighted graphs. We believe like solving this conjecture is simpler than like working with codes. And also, before diving into the details, I also want to mention a few related works. So, in fact, the round restricted feedback channels are only one way of formalizing the concept of limited feedback. There are also other ways. For example, we can consider a constant fraction of feedback, which basically means, say, for every 10 bits Alice sends to Bob, she can request for feedback for at most one of them. And also, we can try to minimize the total amount of feedback sent from Bob to Alice. Like instead of saying we can only have, let's say, 2 rounds of feedback. And besides, there are also some related words on what we call two-way codes, which basically means the test is still like for Alice to send one message to Bob, but they can engage in an interactive protocol where they communicate back and forth over the same noisy channel. So it can be viewed as a way of implementing a noisy feedback mechanism. Okay, now let's go into the proofs. So first, let's see how should a typical erasure protocol look like. So suppose initially Alice wants to send some message H to Bob, which comes from a certain set gamma 0. And in every round I, Alice will send some encoding yi of the message H she wants to send. But because of the adversary, what Bob receives is a corrupted version y prime I. So what Bob can do is he can compute a set gamma I which contains only the compatible code words. So by compatible, I mean the encoding should be identical to what he receives in that round, except for those erasures. At the same time, because of the feedback, Alice can also learn what is y prime I and gamma I. So in the next round, both Alice and Bob know the same gamma I, so they can choose the right code to use in that round. And finally, after all rounds of computation, Bob will just output an arbitrary element of the set gamma I plus 1 because all those code words are consistent with the entire transcript he receives in the protocol. And the resilience of such a protocol is simply the summation over rounds of the amount of erasures required to shrink the set gamma I minus 1 to gamma I. And actually, furthermore, we can see we actually don't care about what are the specific elements of gamma i's. What we do care is only the size of gamma i's because we only want to know what is the amount of erasures required to, say, reduce 5 possibilities to only 3 possibilities. So because of this, we need to study what we call least decodable small codes. So we define the less than k least decoding radius for m code words. denoted by dmk here, such that for all distance parameter d prime larger than dmk, we want to ensure that for all possible codes with m code words, there always exists k-compatible code words using only a d prime fraction of erasures. It basically means we can find k code words which are different only in a d prime fraction of the locations. And at the same time, you also want for all distance parameter d prime less than dmk, we can construct a good code with m code words such that we cannot find k code words which are compatible using only a d prime fraction of erasures. So one contribution of this paper is for erasures, we show the exact value of dmk is this formula for all values of m and k. And you can see this value is increasing in k and decreasing in m, which basically means okay, when we can get a better residence or decoding radius if we have a larger list size or we have a smaller number of code words to encode. And also we know the limit of this value is 1 minus 2 to the 1 minus k as m approaches infinity. And our construction in the paper also shows that we can simultaneously achieve the optimal value of dmk for all k using the same code. And that code is also of constant rate. So now using the holistic codable small codes, we can now see what are the lower and upper bounds for the max residence. Okay, let's first see what are the possible adversaries. So first we consider the simplest case with only one feedback round. We are going to use the following two attacks. So in the first attack, we want to erase 1/2 of the first round of computation. So by the D functions, we can know in this case, Bob will be confused between two different code words. So he cannot distinguish between them after the first round. And we also make the adversary erase the entire second round of communication. So this way, at the end of the protocol, Bob is still confused between two different code words, so the protocol fails. And in the second attack, this time we erase 3/4 of the first round to make Bob confused between three different code words. And now in the second round, we only need to erase a 2/3 fraction of the communication, and Bob will still be confused between two different code words. And if we optimize over a different allocation of communication between two different rounds, we can see no matter how we allocated the communication, the max residence we can achieve is upper bounded by 5/7. And this 5/7 is achieved only when the 4/7 fraction of the communication is allocated to the first round, and the remaining 3/7 is allocated to the second round. And similarly, when there are more than one round of feedback, we will use the following attack. So we first identify the two longest rounds of the protocol. For all other rounds except those two, we'll just erase the entire round of the communication. And for those two rounds, again, we first erase a 3/4 fraction to make Bob be confused between three different code words. And then we erase a 2/3 fraction to make Bob confused between two different code words. So at the end, the protocol fails because Bob cannot tell between two different code words. And this time, if we optimize over all possible application of annotation, we can see the max possible residence is upper bounded by 1 minus 7/12 times r plus 1. And this is achieved when all rounds of computation are of equal length. So what these attacks or adversaries actually tell us is, in order to achieve such resilience, the only way to allocate the computation between different rounds is as follows. So for a single round of feedback, the first round versus the second round, the communication should be 4 versus 3. And when there are more than one round of feedback, the communication should be allocated equally between all rounds. Because if we don't allocate the communication this way, we can definitely not achieve the resilience we get from previous slides. And now the question that remains is why such protocol should be resilient to all possible attacks. Because on previous slides, we only choose specific attacks. But for this protocol to have a certain resilience, we have to ensure that under all possible combinations of the size of gamma I, this protocol is still resilient to such fraction of erasures. So what we show in the paper is the following very technical lemma. So for all K1 larger than K2 larger than K3 larger than 2, such that K2, K3 is not the pair 3 and 2, we show that d of K1, K2 plus d of K2, K3 is at least 1 plus d of K1, K3. And the way we interpret this inequality is that, so whenever you have two consecutive rounds of equal length, from the perspective of adversaries, it's almost always easier to reduce the size of gamma I in a single step instead of doing it in 2 steps. So basically, it means it's always better to corrupt part of the communication in one of the rounds and then erase the entire communication in the other round. So after some calculation and using this specific lemma, we can actually show that, okay, so the protocol we construct on previous slides are indeed optimal and achieves the specific rate we calculate on previous slides. And finally, I also want to mention some challenges for the corruption case. So why it's so hard. So first of all, we do not have an exact characterization for the value of dmk for all values of m and k. What we do know is only the case of k equals 2, which is just unit decoding, which we know quite well. And also from previous works, we know what is the asymptotic behavior of this D function when m approaches infinity. And also using only these 2 results, we can derive a upper bound on the match resilience in the case of r equals 1, but not for r larger than 1. And apart from that, in the corruption case, Bob can no longer compute a set of gamma I, which are compatible with the transcript. What he can only do is to compute the remaining budget, the remaining corruption budget for each possible message X, assuming Alice wants to send the message X. And also note that because this remaining budget can be different for different messages X, now we need to design codes with non-uniform distance guarantees. Instead of saying, okay, for all pairs of code words, we ensure, say, their relative distance is at least the 1/4 apart, that won't be enough because to like in order to achieve the optimal residence, we must have different distance guarantees for different pairs of cohorts. Okay, that's all for the talk. Thanks for watching.